Um, Hi, everyone. Thank you for joining us today. We are hosting Samarth today. He's a research scientist in Intel Labs working on contact-rich robot manipulation, navigation, and locomotion. He did a postdoc with Matthias Muller and Vladlen at Intel, and his PhD was at Georgia Tech with James Hayes. And in general, his interest is in hand-object interaction, human grasping, and contact from contact perspective. We are very excited to have Samar today, and yeah, take us away.
Yes, thanks, Kiana. And hello, everyone. I'm Samarth Brahmbat. Thanks for attending this talk on robot learning and perception for contact reach manipulation. So here is a set of works which I co-authored, which I'm going to touch upon today. Uh, but most of it is going to focus on this last paper from ICRA this year. And as you can see, it's about contact reach manipulation. It's about inserting plate into a slotted holder. Now, we can think about this kind of contact-rich object placement within the broader task of object rearrangement, right? Um, so here, there's a lot of interest in the community about building simulators from which we can learn policies for object rearrangement. For example, I'm showing you here this video from work within AI2, the manipulator environment. Um, and of course, we want to move out of simulators too, right? We want to execute the policies that we have learned from all kinds of simulated and other kinds of data. We want to execute that on home robots, hospital robots, factory robots, etc. Now, when we think about putting these policies on the real robots and breaking down the object rearrangement into sort of the three main tasks, which is grasping the object, transporting it, and then putting it at the target location. Uh, what I found in literature review is that there's a lot of work on grasping, there's a lot of work on navigation, with lots of examples of execution on real robots. Uh, but the last task of object placement remains a little bit underexplored, right? Even if it's something as simple as putting down a water glass on a flat table, uh, we generally don't kind of hover above the table and let the object fall down, right? We want to get that tactile feedback of the bottom of the glass, touching flush with the surface of the table. And we have a really good intuition that we have built up from our experience about how it feels when some object has been placed properly. Um, and I feel like that area of robotic manipulation is a little bit underexplored. And what I'm going to talk about today is a first step there in that direction. So even narrowing down further, in this particular work, we are interested in inserting objects within constrained locations. So things like, I mean, you can think the immediate word that comes to mind is peg in hole insertion, right? That has a lot of research being done over decades. But even around the house, etc., we do this all the time, like loading the coffee mug into a coffee maker or loading a dishwasher and things like that. So here's a slice of related work. As I mentioned, there's a lot of related work in peg and hole insertion, but I'm showing here some of the recent approaches which use which use visual observation inside their policies as an observation of their policies. So one common thread that I found in this kind of research is it needs to have a camera. It needs to have an environment camera, which means a camera that is placed in such a way that it can see the whole interaction without too much occlusion. Now, if we want to implement these kind of policies on mobile manipulators, which have, cameras on their body or maybe on the wrist of the robot arm, uh, such policies which rely on unoccluded views are not that optimal, right? And there are a couple of other issues there as well, um, about how much how much training you need to do on the real robot versus how much you can do on the in the simulation or with offline data, etc. Um, and what is not shown here is also a lot of work on kind of designing uh, what you call impedance controller policies, etc., which work completely from force torque observations, but which are kind of hand scripted heuristic algorithms, which are which are quite specific to the particular peg and hole combination. So what we wanted to do in this paper was was to uh, design a manipulation and a in contact rich insertion policy, which down the line can be applied on a real real robot, real mobile manipulator robot. So if we look at ourselves, we are also mobile manipulators. If we look at ourselves, how we do these kinds of tasks. So if I'm trying to insert this kind of bottle into my backpack, what I find myself doing is first I take a look at the bottle that I'm holding and the kind of sleeve that I want to insert it into, and then get a rough idea of the location, then give it a try. Then somehow from the from the force feedback, I feel that I have actually not managed to insert the end of the bottle into the sleeve. So I backtrack and then get it right the next time. So this is roughly the kind of behavior that we were trying to go for in this paper that we wanted to learn. So yeah, you can see an example of that here, kind of like an execution of the final policy that we have trained. So before going into the details of the training, I just wanted to show how it looks like in practice. So um, as I said before, we are not focusing on grasping the plate. We assume that existing algorithms do that for us. The policy that we have learned starts acting when the robot has already brought the plate in vicinity of the target, right? And the idea is we have this um, a slot which we want to insert this plate into, and the location of that slot is very roughly specified, and roughly in the sense that we don't have millimetric accuracy, because um, in real robotics, even when you try to detect these kinds of insertion locations with image based detectors, etc., those are not completely accurate. So, and there could also be all kinds of unknown obstacles. So here we have tried to make the task slightly more difficult for our policy by putting this kind of obstacle object here in the target slot. And uh, the task of the policy is to deal with these kinds of unexpected collisions and successfully insert the plate. Um, some other constraints, that we put on this policy is that it shouldn't rely on kind of.
Samar,
Yes.
mm, sorry, I'm just going to interrupt you this one time.
Yeah.
We have a question in the audience, and I'm not sure how you would like to handle questions.
Oh yeah. I mean, yeah. Please feel free to interrupt me and ask
Okay,
questions. Yeah.
okay, thank you.
Hi, Samad. Quick question. I'm probably getting a little bit ahead of myself in this talk, and you might come to this, but I'm curious. So, in this, the arm is trying to place the plate in. This seems like some sort of a simulated, or like a dishwasher rack.
Hmm.
Um, and as the robot is placing the plate, I can see some the plate moving a little bit, jiggling a little bit until it makes its way into the slot.
Right.
How much of this, in your opinion and your experience, how much of this can be sensed visually, and how much of it requires tactile sensors? And if you only had one, do you think you could solve the task?
You mean one tactile sensor?
Like if you had either vision or
Hmm.
tactile, is that sufficient, or do you need both?
Yeah, it's kind of like a spectrum, right? If you So here we don't rely on any knowledge of the pose of the object in the hand, right? We have um, now uh, if the object is going to slide by a large amount, then I think the performance of the policy would reduce significantly. But as you can see, if it's if it's just moving around slightly, then these kinds of effects can be simulated and learned from in simulation, and policies are able to kind of deal with those slight perturbations. Uh, yeah, does that answer your question?
I guess what I was asking was, in order for a policy to either be robust to the slight shifts as it makes contact with the dishwasher, or
Mhm.
be able to take decisions based on, okay, it hit an obstacle, so now I need to like take it up and slide it a bit differently. Is
Mhm.
that feedback visual in your work, or is it based on some sort of force sensors?
Yeah, it's based on force sensors. It's based on force and proprioception.
I see.
So currently, there's no visual sensing in this work.
Okay, okay,
Yeah.
thank you.
But I think towards the later end of my talk, I will talk about some ideas about where vision can be helpful and in which conditions it becomes more of a help rather than a hindrance. Um, because one of the things that happens when introducing vision is also all kinds of generalization you need to worry about, etc.
Okay,
So
thank you.
yeah, yeah. So as I was saying, we would like to have we would like to have policies which don't have kind of detailed, classic robotic paradigm where you have detailed 3D models of the object and the slot that you're trying to insert it, and then you're accurately tracking the pose of the object as it's moving, and then you kind of script a policy based on that. Instead, we would like to check the limits of how much learning from simulation can make us robust to these kinds of requirements, right? Now, of course, in extreme cases, we would like to have some knowledge of, let's say, the object has slided by 10 centimeters or something. But if it's within a few millimeters or a few centimeters, then we would like to deal with that without having to model everything. So, uh, yeah. So we, as I said before, we cast this problem as a reinforcement learning. So it's kind of in the broad picture, it's a very standard reinforcement learning sim to real transfer project. Um, but the contribution of this project is more in drilling down into what kind of things you need to do during the simulation training so that these kind of contact rich policies can transfer to the real robot. So I'm going to talk briefly about the simulation environment and how we think about the state of the problem and the action, etc. So we have uh, this classic RL loop where the policy is getting observations from the environment and then executing actions in it. So the observations consist of, um, as I was saying before, the wrench, which is the force and the torque exerted by the robot at this particular coordinate frame at its end effector, as well as the pose of the pose of the end effector relative to where the end effector would be if it were inserting the plate successfully, right? Um, and I'll talk more about how we get this relative pose and how we bridge the sim to real gap in that pose. But for now, just assume that we have that available from the simulator. So we accumulate edge step history of these two observations and give that to the policy. And the policy gives us a target action AT, which just says how much should the end effector move uh, in the next time step. So it gives a kind of a pose target for the end effector. Now, this is kind of a small detail, but inside our policy, we actually have a residual framework where we have a base policy which is kind of blind and just goes in a straight line from the current end effector pose to its target. And then what we learn is actually a residual policy which modifies this straight line trajectory. Now, um, you need to actually execute this policy on the real robot, which is where this operational space controller comes in. So that is not a contribution of our paper. It's a robot control framework that has been popular since I think the late 80s. But what it does is, given a target and effector pose for the robot, it generates the torques that you need to apply to the robot's motors, considering the and kind of negating out the effects of the robot's own the masses of the links and its velocities and Coriolis forces, etc. So all of that is handled by this kind of high frequency control loop, and there's a low frequency policy loop which generates targets for it every five yeah every 50 steps of this high frequency control loop. So that is like the overall architecture in which we execute our policy. Um, and the reward function is also quite simple compared to some of the other related works, which is we want to encourage the agent to quickly finish the task. So there's a constant time step penalty, as well as there's a positive reward for finishing the task, negative reward for negative reward if the plate falls out of the grasp. Mm. And then also, to kind of give a continuous reward, we also give it a penalty proportional to the distance from the target. So in one of the previous slides, I talked about this target pose. The pose of the end effector, where the end effector would have been if it were successfully inserting the plate. Now, that is quite challenging to obtain in the real world, because um, I think, first of all, as the question was saying, um, we we don't have the exact pose of the object in our hand, exact pose of the object with respect to the end effector. So we don't know where the end effector would be when the plate would be successfully inserted. And during the interaction, that pose can change and shift by a few millimeters or centimeters, or a few degrees. Um, Another issue is, uh, in this paper, we actually approximate it by just kind of holding this QR code. But if you implement this as a part of a end-to-end robotic rearrangement system, then you might have an object detector specifically trained to detect slots, for example. And that detector is going to have its own inaccuracy, right? So that's what I'm showing here, that you might have a detection, but it's going to not exactly point you to the kind of gap between the two slots. So how we deal with that during the simulation training is simply by adding random noise to it at every episode. So the observation fed to the policy, which is that relative pose, is calculated by adding random noise to the real target pose of the end effector. Um, so in these next few slides, I'm just going to present kind of a continuous ablation study. So I'm going to present, 4 or 5 different things that we do during our training, and then I'll show directly its effect on the real robot transfer. So you can see here the success rate of the policy, which was calculated by trying to insert this plate in each of these 6 slots with different blocking objects. And for each slot, we executed 4 trials. And then we got these average success rate numbers. There's also standard deviations which are in the paper. But what I'm trying to show here is that if we do not do this randomization, then of course it performs well in simulation, uh, but it totally doesn't transfer to the real robot, right? Because the real world is going to be noisy. Um, Now, here what I want to also highlight is the performance in simulation for all of these methods is kind of tested in a realistic simulation where the observation is going to be noisy. But even if you train with a noiseless observation, when you test it in the noisy simulator, it still gets around 50-55% success rate, but totally doesn't transfer to the real robot. So it has a 0.0% success rate. Now, the next thing that we found to be quite important is how to give it a memory of the states. Um, because a single state, a single observation of the uh, end effector range and the relative pose is often not enough in these kind of contact rich tasks where we want to remember when if I'm contacting right now, we want to remember whether I was going down or up, and those kinds of historical informations become quite important. So we tried out four different kinds of representations, or three different kinds of representations. And what we found works best is to just stack these observations. Of course, it's important to kind of figure out, yeah, it's important to figure out how much of a window we need. And that is kind of a hyperparameter that we need to tune. Uh, but kind of the other thing that comes to mind when we think of history is recurrent models, and we found that at least in this case, the recurrent model performed well in simulation, but not so well on the real robot. So it has issues with transferring to the real robot. One hypothesis is that since we don't control explicitly how much of a history the recurrent model considers, uh, it might, the longer your history window, the more chance your policy has to overfit to kind of these kind of longer patterns, longer trajectories of observations. And if there are small errors or sim to real gaps in each step of this trajectory, then the long trajectory will have a larger sim to real gap. But in general, we found that um, kind of by testing out three or four different values of this window size, we were able to find a good compromise between the size of the observation vector and the sim to real transfer performance. The next step, which was also crucial for transferring, was uh, modeling some of the delays. So um, when you implement these kinds of policies on a real robot, typically there's a policy server, which um, uh, the control node of the robot gets the observation reading from the robot, then sends that observation to the policy server, which responds. So I'm seeing a flicker in my screen. Are you guys able to see my shared screen properly?
Can you move it again? I don't see any. Oh, yes. Uh, yes, it's small, but yes, we can see it.
Okay. Yeah, sorry. So, yeah, as I was saying, there's often a policy kind of client server architecture, and uh, that's often a source of a sim to real gap. And this was an insight that we actually found was quite common in the legged locomotion literature, but wasn't wasn't present in the manipulation literature. So, typically, what happens is this control loop continues to run, and the but while the control loop is running, you send the observation vector to the server. It takes some time to compute the action, and it sends back the action. So that round trip delay time means that you will start executing action AT when the state of the robot has changed compared to the state that was used to get your observation vector, right? So sometime, maybe a few milliseconds elapses. And during that time, the robot still continues to kind of execute its past target. But often what happens in simulators while training this is that the simulation time is stopped while this kind of action calculation is happening. So this kind of modeling of the delay is quite crucial for contact-rich tasks. So as you can see in this graph here, um, it has a large effect on the success rate of the real robot execution. So you can see that also in these kind of example videos where the reactivity, the reactivity of the policy to contact events, etc., is greatly impacted by this modeling. And uh, once it is not able to react, then it kind of experiences a distribution of states which it has not learned during training, and kind of goes off the rails. So yeah, there was a second insight that we had. Now, in by incorporating all of these insights, when we when we train the policy in simulation, this is kind of an example uh, video of the policy executing in simulation. So you can see that we have um, very rough models of the object and slot, etc. So we just have these rectangular slots, a very simple ideal cylindrical plate, as well as the gripper is modeled as kind of a rigid gripper. But if you see some of our execution videos, um, it's actually a soft gripper, which adds a little bit of damping to the forces and torques. Um, we did some work in modeling the gripper as well, but we found that it wasn't necessary for this task. I think for more complicated tasks, we might need to have a model of the gripper that is also flexible. Now, um, here is some comparison to the baselines. Um so we implemented two heuristic baselines and one from the literature. So you can see one baseline which just blindly moves straight down, as well as another random search baseline uh, which is sort of much more reactive. So when it experiences a collision, when it experiences an upward reaction force um, at a at a height, then it backtracks and kind of chooses a random perturbation, a random motion in the XY plane, and then tries to go down again, right? So it's based on these kind of height thresholds, which are dependent on the size of the plate. Um, but often we found, as you can see here in this video, that it's also sensitive to kind of minute collisions that it experiences due to the kind of the curved shape of the slot, etc. And it often gets kind of stuck in these infinite loops. And this other baseline, which is the no vision version of a previous, I think, ICRA paper from 2020, was it had a different architecture of using the range and the relative pose observations, which we found performed quite well in simulation, but also did not transfer well to the real robot. So yeah, I think that's comparison to the baselines. Now, of course, we would like to have policies which can generalize to all kinds of objects, right? And we did some preliminary work on examining the limits of generalization of this policy. But as I'll present later, I think to do much more kind of rigorous generalization, we would need to modify we would need to have some significant modifications to the algorithm. So what we tried is, you can see all the videos that I showed before were with this regular plate, which kind of roughly matches the weight of the simulated plate, although the size is quite different. And we tried to execute the same policy with plates with much smaller sizes, as well as with this cup. Um, And when the size of the object becomes much smaller than what we trained with, um, what we do is to add an artificial offset to the pose observation to account for the change in the size of the object. So for the small plate and the cup, the sim to real transfer is not exactly zero shot. We have to add an artificial offset. But for this regular and medium plate, it's just zero shot transfer. Okay. So yeah, here are some numbers on it. Again, we are comparing the three different baselines to our model in terms of performance in simulation, which is in blue, as well as performance on these different objects, which are in various shades of green. So you can see that our algorithm is able to uh, generalize quite well to the medium-sized plate, and also kind of the performance degrades, but kind of still is much better than the other baselines that we tried. So here are some videos of that. Sorry. Mm. The cup video we found was quite interesting. When we were training this algorithm, we did not even think about transferring it to a cup, but we found that the the kind of state representation that we have, which is this contact wrench and the end effector pose, means that the shape of the object that you're trying to insert becomes less important, right? Because even if it's a cup which is contacting at multiple points on the slot, what happens is it generates a contact wrench at the end effector which looks similar to that from a plate, and so um, the policy is able to transfer that as well. And here is just a quick example of how you might apply this to do some real world kind of object insertion, where we want to insert, where we want to fill the entire holder with different objects, right? So first we insert a cup, and then we try to insert the slot we try to insert the plate in the same slot, but then the policy is able to find a free slot and manage to insert it.
Quick question.
Sure. Yeah.
So, do you mind going back one slide? Okay, so I may have missed something, but you do use visual observation at the beginning of an episode, right?
Yeah, that is true. To get the rough pose of the slot. Yeah.
So, in that case, why does the plate make contact with the cup in such an obvious way? Like, shouldn't
Mhm.
the visual observation tell it that the slots to the left and right are empty?
Yeah, that's a good question. And I think so. Why that happens is because it depends on which slot you point the policy to, right? If you if you hold that QR code to this first slot which is empty, then the policy will go and insert it there. But here, to show the ability of our policy to deal with unexpected obstacles, etc., we pointed the policy to the same slot. um,
Oh, I see. I see.
yeah,
So you tell it which slot to put it in,
exactly.
and then it can sort of overrule that and put it in a different slot if it's occupied.
Yep, yep.
See.
So I think let me show this slide. So you can see it here, where you can do this kind of. This is like roughly holding the QR code at the pose, but this is corresponding to this particular slot. Then, if you wanted to insert it in another slot, you would hold it, uh, maybe on this rightmost slot.
I see. So is there I'm sort of asking this question a little more broadly than uh, just your ICRA paper.
Mhm.
Is Are there other works that you have worked on or other people in the community where vision can be used to sort of chain together successive episodes so that you don't have to sort of manually direct the robotic arm to fill in this slot and this slot. Like vision could be
Yeah.
used to inform you which slots are already filled, right?
Yeah. I think that's a very good observation. Vision definitely can be used. I think. Well, I myself have not worked in, and that would be a really good future direction. I think that was going to be in my next slide, which was uh, integrate this kind of policy with a vision based detector and a high level planner, which plans a sequence of insertion episodes, etc. um, I think if you look at all the line of work that comes out of that DARPA robotics challenge, that's at the top of my head. I can think of those papers where they have to detect, for example, the door handle, etc., and then go and manipulate it. Um,
I see.
yeah.
Okay, thank you.
So, okay. I think, yeah. So let me go back to this motivation slide that I presented earlier, right? Because I want to highlight one unique challenge that we face when we try to implement these policies on a mobile manipulator, which is mobile manipulators usually have cameras on their bodies or on their, at the shoulder level or the wrist level. So the contact surface is often hidden from that egocentric perspective, right? And even possibly there could be kind of a higher uncertainty in the pose of the target location where you want to place the object. Let's say that target location is specified in world coordinates, but you are tracking your mobile manipulator while it is moving around using some kind of particle filter or something. So there's going to be an inaccuracy in the pose of the robot with respect to the world. Um, so both of these cases, the pose uncertainty as well as the contact surface hidden from egocentric vision, means that when we want to execute such policies on mobile manipulators, we need to think carefully about how and when to use vision, and we also need policies which are able to deal with this level of uncertainty in poses, right? Um, so again, coming back to those related works, uh, such kind of environment cameras are a little bit not very applicable to the mobile manipulation scenario. So um, some of the ideas, so we haven't worked on this, but some of the ideas which I would be quite interested in exploring in the future are, uh, as you said, integrating this into a higher level system, which can, load an entire dishwasher, etc. But also use vision to condition the policy on some information about the object and the receptacle, right? It could be something like um, just we still don't need a full 3D model of the object, but it could be something like, if we are able to segment out the object, then we can have a rough idea about how long the object is or how wide the slot is, etc. And that kind of information is not something that is changing at every step of your episode. Instead, it's something that you can get from a snapshot before the start of the episode, and then you can feed in as a conditioning variable to the policy. And that way you can have a policy that can generalize to different conditions. And I think another very interesting direction could be uh, how to kind of pre-train or pre-learn some of these behaviors from the large amount of offline data that we have, right? For example, internet videos. Now, of course, learning in simulation and transferring to the real robot is quite powerful and works when you're able to um, recreate that simulation. But uh, there are lots of other tasks which, for example, we do around the home or kitchen, etc., where it becomes quite tedious to design uh, kind of very diverse manipulation environments. And so, if we are able to find some ways to learn from existing data of humans doing it, then I think that would also be great. So, one example of that is uh, is, for example, these kinds of data sets which are becoming quite popular in the vision community, where there are there's a large amount of egocentric video of people doing various contact rich manipulation tasks. Um, and as you can see, there's a large frequency of these video clips which deal with putting objects, on various surfaces in various cupboards and shelves, etc., and in general, living objects. So I feel like while robotic object placement is unexplored from the point of view of heuristic design of placement policies, there's a lot of data in the vision community, but we still need to find ways to make it accessible for robotics, right? So for example, if we want to do imitation learning on it, or even treat it as a data set for offline reinforcement learning, kind of a basic requirement for that is to pass those videos into trajectories um, of the at least the object pose trajectories, right? So we want trajectories of where the hand is, where the object is, and if possible, even the contact range that the hand is exerting on the object. So that is where I think the connection can be made to computer vision. So, and that's where I'll quickly talk about some of my previous work. So I think I'll go very quickly through this. So we in 2019 we came up with this method of um, observing contact through a thermal camera, because the heat left by the hand on the object can be sensed with a thermal camera. And then in a follow-up paper, we designed a system with multiple kinects, etc., to be able to capture hand pose information and RGBD images along with this kind of object contact maps. So the final format of the data is like following, where we have these 3D models of the objects with along with where people touch the surface of the object and the hand pose as well. So how can we use that contact data in the framework that I described, which is, if you look at kind of off-the-shelf methods to estimate hand pose and object pose from these kind of manipulation videos, we find that there are large inaccuracies even in the ground truth. So here is, for example, ground truth from the HO3D dataset. So the fingers are often kind of hovering or penetrating, and if you apply kind of state-of-the-art hand pose estimator algorithms, then we find that the accuracies increase even more, right? So we found that reasoning about the hand object contact results in hand and object poses which are much more accurate, and those traces can be used to, for example, learn policies potentially in the offline RL framework. So um, yeah, I'll quickly go through these slides where I'm trying to describe uh, a method for integrating a contact map. So if we assume that a contact map on the surface of the object is available, then we can run this kind of iterative optimization algorithm where we start with, for example, the hand pose, which is estimated from an image. And then we use this kind of differentiable hand mesh generator, like, for example, this Mano model, to get a kind of a contact map corresponding to the current hand mesh, compare it to the input contact map that we have access to, and then do gradient descent on it to kind of update the hand parameters. So um, of course, for that, we need this kind of contact model, which we have developed in our ECCV 21 paper, ECCV 22 paper. But I'll not go into the details of that. Instead, I want to show you kind of it working in practice, right? So we have, um, so we have this kind of model where we first estimate the pose of the object. Then we use this deep contact model, which is trained using the data that I showed you before, where we kind of add random perturbations to the hand pose, but we have the ground truth contact map on the surface of the object, right? So with a noisy hand pose, we can still predict using a point net architecture. We can still predict accurate contact maps, and then those contact maps, which are estimated here, can be used in this iterative framework to improve the pose of the hand and the object. So uh, here is just that optimization working in practice. I think, yeah, in practice, we found even it was able to correct even larger errors, as you can see here. So in the first row, you can see that image-based pose estimates are, off by a large margin. But when we do this kind of contact-based optimization method, we can get um, much more accurate results. Now, uh, yeah, coming back to this motivation of using video data to generate data for learning contact-rich robot manipulation. We talked about the pose of object and hand, but another component that was at least needed for our policy was the contact forces, right? Um, and uh, just very briefly, I mean, in the literature, there are a couple of ways people have done that. For example, there is work about estimating contact points and forces based on the motion that you see, like motion of the object that you see, because finally the end effect of the forces that the hand is applying should result in the motion that you see in the next frame, right? What we have investigated is doing this kind of force estimation based on appearance, where we found that there are subtle changes in the appearance of the hand, which correspond to how much force is being applied by that part of the hand. So you can see that. Here, um, where we use this kind of a planar sensor, which is able to give us these pressure values and collect data from this kind of capture setup, where we collect pressure values along with RGBD images. So you can see, yeah, some of that data being collected here. We collect the data from various perspectives. We invite a large number of participants with diverse skin colors and different hand properties to collect this data, and then we train a supervised learning model to predict the contact force and location between the hand and the object. So you can see here how, as the person applies force using different fingers, the model is able to pick up on these subtle changes in the shadows, the hand color, etc., to predict the force. Now, of course, one limitation is that we are only predicting the normal component of the force, but in practice, we need to do much more work to actually estimate the full contact, the shear forces as well. But I feel like this is one step in that direction. And to summarize, we first talked about a real robot implementation of object placement, and specifically inserting objects, which is an important part of a robot that can do full stack object rearrangement. And towards the end, we also talked about some perception work for parsing states and action from videos, which down the line can potentially be used to learn many robot manipulation policies. And I think that's an exciting area of research, which is also getting a lot of attention right now. So I would also like to thank a lot of the collaborators. A lot of the code of the projects that I mentioned is available open source. And I'll just play this video of the various trials of insertion that we did while I take some questions.
Cool. Thank you for the talk. Do we have any question from the audience?
Yeah, I could
Fabian?
ask I had a couple questions. The
Mhm.
second one's a bit silly, but the first one is just, yeah, you talked about all of these different parameters that you had to tune in the first work, like the noise model, the length of the history, and the inference delay.
Mhm.
And yeah, I was just wondering how you how you think you can identify and tune these crucial parameters across many different tasks, because it feels like it'd be cost prohibitive to manually go in and try to figure out which ones are important and tune them for every task.
Yeah, I mean, that's a good question. I think some of the, for example, the delay parameter, the range for how much delay we want to randomize, uh, some of that can be done by system identification, right? We can execute any kind of dummy policy on the real robot and see what is the round trip delay and identify that. Um, but I think the larger question about identifying the other hyperparameters, I think, yeah, at this point, it's mostly a question of trial and error. But I haven't worked on such projects before, but in the literature, uh, people have done kind of like a outside loop around this training. So there's a lot of interest in meta reinforcement learning, for example, where you do a little bit of interaction with the environment to estimate a vector which summarizes the parameters of the environment, which is not kind of human interpretable, but the assumption is that these parameters are able to condition the policy for that particular environment. So I think meta RL is one task, one approach for that. Of course, it increases the computational burden because you need to train for much longer. Um, but I think you can get hints from vision as well. You can use, for example, uh, simple kind of heuristics derived from vision to get some idea about the size of the objects, etc. Yeah.
Okay, got it. Yeah, thanks for the answer. The other question I had was just, what's the material of these plates and cups? Is it ceramic or plastic or what?
It is not ceramic and it's not plastic also, but it's kind of like a thin ceramic, I would say. Uh, like it's not that heavy kind of ceramic. You know what I mean? And that's actually a very interesting question, because one thing that I forgot to mention is we also try to execute this same policy on, for example, a book. For example, this kind of a hardbound book, because it also has a similar kind of plate-like shape. And we found that these books, they are made with much more flexible material, and the policy does not transfer well because it kind of changes the profile of forces and torques. So that's another, um, area where kind of information about the object that you can get before doing this episode, you can feed it as a conditioning variable. And there's a lot of work on kind of estimating material from vision, or material from tactile sensor, etc., that I think can be integrated to estimate the material of the book. Yeah.
Okay, thanks.
I have a question. These are all amazing work in grasping. The community has shown some progress in navigation. And what are your thoughts on the like the next 5-year direction of the research aligned with with this type of grasping that you're doing?
Mm.
How would you think will proceed moving forward?
Yeah, I mean, I think uh, first of all, we are seeing much more powerful neural network architectures which are able to reason about sequences of data, for example, transformers and that whole line of work. So I think personally, we had to spend a lot of time kind of figuring out the right representation of the history. And I think we could see these kind of architectures maybe even uh, getting giving us a better ability to reason about trajectories, because fundamentally, all these robot RL, etc., is about not a single frame but a trajectory of observations. Um, so that's one. And more broadly, Um, yeah, more broadly, I think in the community, what I've seen is there's a lot of interest in this kind of last centimeter, or like contact rich tasks, whether it be insertion or in hand manipulation or things like that. But uh, in if you think about five years, I think uh, personally, I feel like there could be a lot of work on policies which are more generalizable to different robots, not just one particular robot that you have. So, for example, there's work in cloud robotics, for example, at MPI, I think MPI in Germany, where they have made this cloud robot available for anyone to access through an API. And I could see, for example, a long-term effort where there's a set of these manipulator robots, and people are able to run their contact reach manipulation algorithms safely on a set of these robots and test out policies that work on all robots. Because even if you get a different robot of the same model, it's going to have different joint frictions and inertias, etc. Um, so a lot of the policies, what happens in this sim to real loop is that you train in simulation, then you try it out on the one robot that you have, and then you fine tune your simulation again to improve it on that one robot you have. But it will work well on that one robot, but when you give that policy to somebody else, just with that same Franca arm, it might not transfer. Um, so I feel like as this single robot work matures, uh, there's going to be more work on kind of multi-robot generalization, maybe through the cloud path, maybe in individual labs. I'm not sure about what path that would take. But yeah, to summarize, more contact-rich manipulation and more kind of multi-robot generalization.
Thank you. Do we have any other questions? We are almost over time. But okay, cool, great. Thank you so much for the talk, Samarth, and we'll see you later on one-on-one today.
Okay,
Bye.
yes. Thank you. Thank you very much. Thanks, everyone.